Hi guys, now that we've covered the basics of gradient and how we know hopefully quite clearly now that the gradient is dictated by the vertical change divided by the horizontal change, we want to kind of look at the National 5 level equation of a straight line, and that obviously includes the gradient. Now the basics of what we're looking at now are the actual straight line formula. So the general equation, or sorry, should I say equation, of a straight line is given by y equals mx plus c, as you can see highlighted in red. Okay, where the m, as we've mentioned before, is the gradient. Now the c is what we call the y-intercept, and that's simply just where the line, or any line, cuts the y-axis, if in fact it does. So there will only be a c if the line cuts the y-axis. Okay, so those are just the key terms that we're going to have to get familiar with. Okay, y-intercept is an important one, and the lettering, the c and the m. Now the gradient formula that we've looked at before, the m equals v over h, that actually dictates the new formula. And I think I said to you before that when we have missing coordinates, the formula will change, and we'll look at it in a slightly more complex manner. So if we focus now on the diagram in the second half of the note that you can see here, we've got 2 points. Now I've not labeled those 2 points, but I'll do that now. Let's say we have A and B. Now we don't actually have the numerical values for these points, but what we have is we have the y and x values, sorry, x and y values for both. So point 1, okay, which is point A, will be the first point. That's why this one is called x1 and y1, because it's the first point from left to right. Point B, we've simply got the second x coordinate and the second y coordinate. That's where we get the 2 from. Now, it has to be said, when using the formula, the order in which you use, whether you're working from A to B or B to A, doesn't impact the gradient massively. However, the selection of x1 and y1 and x2 and y1 is very important. So we need to make sure we go through a process where we label correctly and we therefore use the right values in the formula. So looking now more simply at actually the diagram that we have on the left-hand side, this diagram here, I want to focus a little bit on that, and then we'll come to the formula. Okay, just so it's easier for us to look at it, I wanted to kind of zoom in on the diagram. What we're going to look at is the vertical change and the horizontal change. And I did mention when we talked about the gradient that was the important thing to look at. It was the change on the vertical axis and the horizontal axis. Now, we did it with numbers, and when we were looking at the difference between two numbers, it was a subtract. So you'll notice straight away on both the diagram and in the formula, we have a subtract. And that's because we're looking at the difference between a horizontal value and a vertical value. And we know from lower school that difference in maths means subtract. However, ultimately, I want to kind of, without getting over complex with detail, I want to look at the green portion here, that change, which we know is a vertical change, and the red portion here, which we know is the horizontal change. Now, it's important to recognize that that change comes from the start and finish of where the points are, not from the origin, not from any other part on the axis in green. It's from where these 2 points are actually situated. So if we focus primarily on the vertical change, first of all, what we've got is a y value and an x value for this second point, okay? So the y value for the second point is y2, the y value for the first point is y1, and that vertical distance that we've looked at from here to here if we were doing it like we had in the previous example, we were either counting up the boxes or working out the difference. And to do the working out the difference, we did the subtraction. It's the value at the top, which is the y2, take away the y1, and this would give you a numerical value for that distance in green. Okay, now likewise, if we take the x values and we're looking at this distance here, we have an x2, which is up here, and an x1, and therefore that distance that we're looking at in red is the difference between x2 and x1, which is x2 take away x1. Now that seems a little complex when you're looking at it with all the y's and the subscript, but when we go into the numerical values, it become a lot clearer. But ultimately, what that does is it takes our formula that we had before, m equals v over h, and it swaps it into this far more mathematical looking formula where we've got y2 minus y1 over x2 minus x1. And all that means is that the difference between the y values was the v, and the difference between the x values was the h. So the formula is the same, it's just a little more complex looking, but it will not be so when you start looking at the actual values. And that's what we'll do now. We'll look at some examples on how to calculate the gradient. Okay, now if we take a look at the first example on how we substitute into a formula. So the formula we are going to be concentrating on, like I mentioned previously, was m equals y2 minus y1 over x2 minus x1, and it's highlighted there in red. We're going to substitute the values from the points we're looking at, and that will allow us to calculate the gradient between those 2 points. So calculate the gradient of the line joining the following points. The points we're going to look at in this example are the point 2, 3 and the point 4, 9. Now, first of all, before we start anything, step one when dealing with this type of thing, this type of question, is to label the coordinates. Okay. We've actually already done that in this example, so I want to show you it. What we've got is we have labeled the first point, which is here, and we've taken the x1 and y1. Now, the reason that's called x1 and y1 is because the point that we're looking at here, 2, 3, is considered the first point. Okay, so the x coordinate on the first point is 2, the y coordinate is in the first point is 3, so x1 and y1 are above the 2 and the 3 respectively. Same in the same vein, the second point we have an x value and a y value. So x2 is 4, which is the second point, and y2 is 9, which is also the second point. Once we've done the labeling like that, it's far easier for us to transfer into the formula. So now, step 2 would just be simply inputting or substituting into the formula. Okay, so sub into formula, and that's what we're going to do. Now, I'm probably just going to highlight these to make it easy to see. So the formula obviously starts with a y2 minus y1. So our y2 is the 9, our y1 is the 3. Hopefully, it's clear to see that those values are just going to jump straight into the formula, which in this case, the y2 goes to the 9. The y1 should go in here, or in fact there. So we've got 9 take away 3. That gives us our 6 as the difference between these two points on the y-axis. Likewise, we do the same for the x values. So we've got x1 and x2. So they're going to jump straight into the formula in the same way. x2 is a 4, so it's going to go in here. x1 is a 2, so it's going to go in like so. So 4 take away 2 gives us our 2. Now what happens at that stage is we have now got the values substituted neatly. We've now got a fraction, as you can see, highlighted in red. It's 6 over 2. we know that 6 over 2 becomes 6 divided by 2, and that gives us 3. So we can say the gradient of the line that joins 2, 3, and 4, 9 is 3. Now, I want to mention, obviously, now that we've got it, it's the wee recap. That would mean, in a very simple sense, it's a positive value for a gradient. So although we don't know yet what the y-intercept is, we know that that line's going to go in an upward direction from left to right. Example B, very similar process, so I won't go through the highlighting and the labeling. I will maybe just show that we've input the values. Now, the reason I want to show the second example is we're going to encounter double negatives. So we need to remember from our integers rules that a positive and a positive will give us a positive and a negative in any order, whether it's the negative comes first or second, will always result in a negative, and two negatives will give us a positive. So once we remember those values, or those, simple integers rules, we can apply them within the gradient formula. Okay, so first of all, let's get our labeling done. I've rewritten the coordinates here, but there's no harm in doing it above the coordinates as they exist. So for example, this would be x1 and y1. This would be x2 and y2. We've obviously already done that for you. So we've got our labels. That's important. Make sure you get them correct. We're going to substitute into the formula. The formula, as we have seen previously, is still m equals y2 minus y1 over x2 minus x1. So now that we've got those values, we can substitute. So let's have a look. y2, forgive me, y2 is -2, y1 is 5, x2 is 4, and x1 is -3. So what we've got to notice here is that clearly it's not as straightforward as having 4 take away 3. What we've actually got is we've got 4 take away the -3 value, and it's always useful to put that -3 in a bracket. So when it comes to processing that formula, we can't just jump ahead and say 4 take away 3 is 1. That would make a huge difference to the gradient. We still have to apply our integer rules. So at the top, it's a little bit more straightforward. At the bottom, still a little more complex due to the integer rules. So -2 minus 5, hopefully we can see from here, -2 minus 5 is going to give us our -7. The 4 minus -3 becomes positive. So that's 4 plus 3, which gives us our 7. We also know that our -7 divided by 7, that's -7 divided by 7 because it's an over. A negative divided by a positive will give us a negative value. 7 divided by 7 is 1, and therefore our gradient is -1. And like I did previously, if we think about what that's going to look like on a graph, it's a negative value. So the line, although we don't know the y-intercept, will go downwards from left to right. Okay, that's substituting into the gradient formula. That's just the first part of the straight line. Once we get used to that formula, and then we can start looking at the equation of a line in full, and it makes life a whole lot easier. Okay, now we should be able to combine our understanding of the gradient and the y-intercept to come up with an equation of a straight line. Now, this example is going to be an example where you're asked to calculate the gradient, the equation of the line, but you have to calculate the gradient and you can physically see the y-intercept on the graph. So hopefully you'll recognize from just looking at this, the y-intercept is the point where the line crosses the y-axis, and in this case the value is 1. Okay, so that's the c value that we've mentioned. The y-intercept is the c value where the line crosses the y-axis. Now, we don't always get given that. For the little work that we've done so far, that'll be the first time you've seen it. So it's important to remember y-axis, or where the line crosses the y-axis, is the y-intercept, and that's represented by the letter C. It's very rare that you'll get something as straightforward as this if it was to come to an assessment at National 5. But I do want to allow you to see it. So the portion of the work in here that you'll recognize, hopefully, and we can kind of go through relatively quickly, is this portion in red here where we're calculating the gradient. Now, what you don't see on here is that there will have been the diagram given where we've got the points 0, 1 and 1, 3. You would then write them out and label above as I've shown you in the past. Then we substitute in, we've got our 3, take away 1. We've got our 1, take away 0. We get 2 over 1, which it changes to a divide, and therefore the gradient is just 2. Now that rings true because what we've got there is on the diagram a positive gradient from left to right, as you can see going with the red cursor. So that's a positive gradient, and we know from the diagram that it crosses, as I've already shown you, at the point 0, 1. Now a y-intercept can be shown in two ways, okay, and this is something that we want to touch on. The y-intercept can be shown just as the value c equals 1, but that represents a coordinate on a diagram, and every y-intercept or every line, every point that crosses the y-axis will start with a 0 x value, because obviously it doesn't move off the 0 point on the x-axis. So y-intercepts 0 and the given number. So 0, 1 tells us c value is 1. We now have to do a pretty straightforward substitution where we have the gradient, forgive me for that, I don't know what's happened there, where we have the gradient, which we've already calculated as m equals 2, and the c value is 1. We need to substitute into this equation y equals mx plus c, which is the standard equation, and we know the m is the 2, so that goes in place of the m, and the c is a positive 1. So it gives us the equation of that line is y equals 2x plus 1. Okay, just as a quick add-on to the previous slide, we had a look at finding the equation of the line in the graph, and it was 2x plus 1. Now we will be asked, rather than just to find the full equation, once we're given an equation like this, we could be asked to state what the gradient is or what the y-intercept is. So what we'd be looking to do is, first of all, make sure that the equation is in the standard form, y equals mx plus c. From there, you can connect the 2 and the m, so we can say the gradient is 2. Likewise, c equals 1, and we know that any y-intercept can also be described as a coordinate, so 0, 1. If I was to take another example very quickly and just give you an equation that read 5x minus 3, then we would be looking to imagine that we had the standard form above, and from there, hopefully, you can see the connection between these values. What's important here is to recognize that there's a negative in front of the 3. So in this equation, we have the gradient is 5, the y-intercept is minus 3, and of course, that would be 0, minus 3 as a coordinate. Now, we're going to look at that in more detail, and specifically, we're going to look at the questions where they don't give it to you in the standard form y equals mx plus c, and what we need to do to extract the gradient and the y-intercept from equations in that form. Okay, extracting the gradient and the y-intercept from the standard form of y equals mx plus c. A little thing I want to explore very briefly with you just now is the effect of gradient on parallel lines. It's quite a straightforward fact. Any lines that are parallel will have the same gradient. So if you're given two sets of equations and you can extract the gradients and they are equal, then you can say confidently that the lines are parallel. If they don't have the same gradient, then obviously they are not parallel. Now, what I actually we'll look at that in more detail in a second, but what I actually want to look at for the time being is what do we do to extract the gradient and the y-intercept from an equation that is not in the standard form y equals mx plus c. And if we look at the example below, we have y equals 3 minus 2x. So it would be very simple to just automatically pick the minus 2 as the gradient and the 3 as the y-intercept. And actually, in this example, it will work out like that. However, that's a dangerous tact. We don't want to be trying to guess these before we rearrange the equation. So I'm going to do a little bit of work on rearranging the equation, and I'll show you how we then extract the gradient and the y-intercept. Oh, okay, so if we start with that very simple equation as example 1, we had y equals 3 minus 2x. Now what we want is we want the equation in the standard form mx plus c. And as you can see here, the x and the numerical value on its own are in the wrong order. Now this is an easy fix for this example, because what we can do is we can just rearrange the order. The -2 will still need to be attached to the x, and the 3 goes to the n. Now what we've got now is we've got a missing sign at the front of that 3. Now we know if there's no sign at the front, it's positive. So in this case, we can now confidently say the gradient is -2, the y-intercept is 3, and or the point is 0, 3. That one, nice and straightforward, however, not always as straightforward when we see it, and we'll have a look at that in the next examples. Okay, if we look at a slightly more complex example, I've got the summary of our first example at the top. As I say, slightly more complex. We're going to look at rearranging 3y minus 6x minus 15. Now, obviously, what we've done with changing the subject is we've always kind of stuck with opposite side goes to the opposite operation. And so obviously in this case, we're looking at multiplications, divisions, additions and subtractions. Shouldn't be all that complex, but we'll go through it as slowly as we can in the first instance to see how we extract the values. So I would always like to keep the equal sign where it is. We want y to stay on the left-hand side, and ultimately what we're going to do is we're going to move this -6x and this -15 to the opposite side. They're both negative, so we can move them with the +6x, but obviously when it's plus, we don't tend to put that plus sign in there. So that 6x can come over, and then because it follows an x, we'll call that plus 15. So all we're really doing is we're changing the side or the opposite side, and we're going to attach the opposite operation to it. At this point, the operation is harder to see. We know that 3y equals 3 times y. So if we're going to remove the 3, we're going to have to do the opposite of a multiplication, which is a division. Unfortunately, both these values were chosen because they can divide by 3 in the first instance. So 6 divided by 3 is 2x, 15 divided by 3 is 5. So we now have an equation in its standard form. We've got y equals mx plus c. In this case, the m is 2, the c is 5, or as a coordinate, 0, 5. Right, now we'll look at examples 3 and 4. I'm not going to write these ones out this time. I'm just going to talk you through them. So the technique stays the same. We want to get back to y equals mx plus c. So for example 3, you can see that we've got y minus x equals 3. We're going to do the opposite side and the opposite operation. So that negative x becomes a positive x. The positive 3 becomes a negative 3. And from there, it's relatively straightforward to see that although there's no value at the front of the x, we know that that is 1. So that's where we get the gradient is 1. In this case, we need to remember that we're bringing the negative sign with it. So that's -3, and the y-intercept can always be a coordinate, so that's 0 and -3 also. Question 4 is a little more complex again, much like question 2. There's more to deal with, but what we have here is we have 2y minus 4x plus 7. So in the first instance, what we would do is we would remove or move the 4x and the 7. So ultimately what we've got is, to start off with, we've got the y on the left-hand side alone, the x and the number on the right-hand side, and then obviously we just need to take the 2y down. The opposite operation to 2 times y is a divide, and this occasion here, or should I highlight it? What we've got is we've shown the division as a fraction, so 4x over 2 is the same as a divide, and what that does is it gives us our final answer, which is y equals 2x minus 7 over 2. Obviously, some of you might want to change that to 3.5. I would avoid decimals at this stage and stick with your fractions if you can, but if you write 3.5, that's not wrong. And then obviously we just take the gradient is 2, y-intercept, or c, is 7 over 2, and the coordinate, as before, can be seen as 0, 7 over 2. So now, last thing I want to show here is the parallel lines. Okay, now question 2 earlier, we saw that the gradient was 2, and in question 4, again, also the gradient is 2. So we can see from rearranging these equations that question 2 and question 4 both result in the gradient of 2. So therefore, we can say from these examples, the lines in question 2 and question 4 are parallel. And it's that simple. From what you see on the screen, if we were to take question line 3, oh, sorry, forgive me, that's come up as highlighting. If we were to take line 3, and the gradient there is 1, and line 4, and the gradient is 2, so we can say not parallel. But from the previous example, the gradient in question 2 was also 2, so we can say if they're both 2, then they're both parallel. It's just a little additional point, and you may be asked to rearrange equations to discover if there are parallel sides. You may just be given an equation in the standard form and asked to decide if they're parallel lines, and the contributing factor, or the deciding factor on that, is if they have the same gradient, then they are parallel. It did occur to me it is worthwhile having a look at the actual equations that we mentioned that are parallel. So in the first instance, in question 2, the equation was given to you in the form 3y minus 6x minus 15. And in question 4, it was given to you in the form of 2y minus 4x plus 7. And I believe that both were equated to 0. Now, it's clear when you look at this type of question, if I was to ask you now, are the two lines parallel based on what we see in front of us? Now, I don't think the best of you could take a guess that the gradients are going to end up the same. What you might do is you might be able to recognize that, you know, there's numbers in front of an x. You might take a guess that the gradient of the first example is -6, and the gradient of the second example is -4. But what you're not going to be able to do is straight away and look at this -6x, and this -4x, and realize that at some stage they're going to eventually end up as a 2x. Okay, so looking at it without the rearrangement, it's really tricky and it's nigh on impossible. So that's why we need to rearrange into the standard form. And obviously, once we've done our rearrangement and we have 2x plus 3, y equals 2x plus 3, and we have y equals 2x minus 7 over 2, in that form, it's nice and easy to see that we've got a 2x and we've got a 2x. The y-intercept doesn't impact on whether the line is parallel. What we're looking for is, do the lines have the same gradient? And once we've rearranged them, it's quite clear to see that question 2 and question 4 have lines that are created that are parallel. And without the rearranging into the standard form, it's impossible for you to have a bash at that question. So hopefully that clarifies things when they're right next to each other. I realise splitting up in the last few slides might not have made it all that clear.